Welcome to the first module of the HP FEM course. After this session, you will be able to explain how physical phenomena in different fields can be described by the same mathematical model. You will be able to connect some fields of science to the study of particular partial differential equations. We will explain the concept of a Galerkin method to compute approximate solutions to a general PDE. And we will explain the concept of a finite element method. Mathematical models and computer simulations are central in science. In fact, the scientific method is often presented in the form of a hypothesis to be tested in experiments. Here, a common form of a hypothesis is a mathematical model. Computer simulations corresponds to a virtual experiment which generates predictions based on this mathematical model. These predictions are compared to physical experiments to falsify, accept, or refine the hypothesis. Computer simulation based on mathematical models can be used to complement or even replace physical experiments, and this opens for many applications in society. New products can be developed based on fast and cheap virtual prototyping. Urban planning is based on simulation of the complex system that is a modern city. Simulation is also becoming a new tool in medical diagnosis and treatment planning. Some common mathematical models include particle models, used to model molecular dynamics of the solar system. Compartment models, to model chemical reactions, population dynamics, or epidemics. Continuum models, describing the mechanics of solids, liquids and gases, and electrical and magnetic fields. And statistical models, where we also take into consideration population variations and model uncertainty. In this course, we will focus on continuum models, which describe fundamental scientific phenomena, such as dissipation, the conduction of heat, or the spread of pollution in the ocean or the atmosphere. Waves, ocean waves, acoustic waves, or elastic waves in the ground in an earthquake, and vortices found in the blood flow in the heart, in the airflow around an aircraft, or as a tornado or a galaxy. Continuum models can be expressed as partial differential equations. Dissipation is described by the heat equation, waves by the wave equation, and vortices by the Euler equation. Some of the most famous partial differential equations also define scientific fields. The study of inviscid flow is also the study of the Euler equations, viscous flow, the Navier-Stokes equations, electromagnetics, Maxwell equations. The Schrödinger equation describes quantum mechanics, and the Black-Scholes equation can be used to price options. To make predictions from a continuum model, we can use computer simulation, which corresponds to the construction of solutions to a PDE. A powerful idea is to extend the techniques of linear algebra to the field of partial differential equations. We can define what we refer to as a weak solution to a partial differential equation as a function that satisfies an orthogonal projection of the PDE onto a vector space of functions. Only finite numbers can be represented in a computer. Therefore, we need a numerical method to construct approximate solutions to the PDE. We construct an approximate solution as a linear combination of basis functions in a finite dimensional subspace. That is, we write the approximate solution as a sum of coefficients times basis functions. In the Galerkin method, these coefficients are determined by an orthogonal projection of the partial differential equation onto the finite dimensional subspace. This leads to a matrix equation, where the unknowns are the coefficients in the linear combination. This matrix equation can be solved by standard methods from linear algebra. A finite element method is a Galerkin method, where we choose the basis functions to be piecewise polynomial functions defined over a mesh, which approximates the geometry of the problem. In an adaptive finite element method, the basis functions are automatically chosen by the method to optimize the accuracy and efficiency of the computer simulation.